start with a second talk. We were very happy to have A.Olgiati. He's going to talk about bosons in a double web, violation of central limit theorem, and energy expansion. So please.
Thank you very much. Yeah, and thanks to Karen Marcello for allowing me to be here and present my work. Yeah, I will present a recent result obtained together with Nicolas Free and Dominique Spener about bosons in a double web. Okay, so the main setting I will discuss is the one of bosonic mean field in the Euclidean space. So I think most of you should know that the mean field is like the simplest or one of the simplest approximate models with which you can extract information from a system. And it boils down in its essence to assume that you impose that particles are independent and identically distributed. And therefore you can, to the leading order, approximate your system with your model with a one-body model. And our aim is to go beyond that, to consider a system in which more than one mode matters to the leading order. Okay, so let me say very quickly in a few slides what some of the known facts about bosonic mean field, which will hopefully help us transition to the model we studied. So this is the Hamiltonian, standard Hamiltonian for bosons in the mean field, and mean field limit is imposed by the coupling constant 1 divided by n. I'm assuming that I'm taking a trapping potential, which is regular enough, and an interaction which is positive and of positive type, and also regular enough. So the ground state energy is unique and well defined, and the ground state as well, up to a phase. Okay, so the effective model that matters is the Hartree model or mean field model, which is obtained by restricting the model, the Hamiltonian, to the states in which all particles are in the same U. And yeah, this is the definition of the Hartree functional. And again, here we can consider its minimum, E mean field, and its minimizer, U MS. These are the crucial quantities to the leading order. And the next to leading order, well, at this effective level or classical level, the next to leading order is captured by the Hessian of the Hartree functional. Okay, and at the quantum level, one can suitably second quantize the Hessian to obtain a quantum operator, which is called Bogoliubov Hamiltonian, which is the energy operator for particles which are not in the Hartree minimizer. Okay, so just to very quickly write a known theorem. So these results were at least obtained in these 3 papers, and then many others. So the n-body ground state energy is given by n times the minimum of the Hartree functional to the leading order, and then plus the minimum, actually, minimal energy of the Bogoliubov Hamiltonian. So there is this splitting. And then another known fact is that the ground state exhibits Bose-Einstein condensation onto the Hartree minimizer. So approximately n particles occupy the Hartree minimizer. Now, much more is known about this model. I would say that by now it is very well understood. But yeah, the main catch I wanted to point out is that the leading order particles are very well described by the I at D picture. And the last known results I want to recall is the central limit theorem. So in the same model, if you take reasonable one-body observable and you define okay, so O is your one-body observable, you subtract its average, its expectation on the Hartree minimizer, and then you make it n-body and you divide by this square root of n. So this is the fluctuation operator, the operator calligraphical, which describes fluctuation with respect to O. Then this, in expectations on the ground state, behaves very much like a Gaussian random variable. Okay, so if I take the expectations of this calligraphical, these are very close to expectations of a Gaussian random variable of the center, so center is 0, and with variance of order 1. So, okay, even here the result is much more detailed. I mean, many more things can be said. Here I'm quoting 2 statements in slightly different settings, but okay. This, I think, is very. This in the statement that I'm citing also holds more trivial than these papers. And okay, so and yeah, the catch here is that the ground state for a bosonic main field satisfies a central limit theorem with fluctuations of order square root of n at the size square root of n. Okay. Now I would like to transition to the system we really studied, which, as anticipated, two modes are to the leading order occupied, and this, at least intuitively, gives rise to more interesting phenomena, because you can consider, for example, states in which the system still condenses in a linear combination or combination of two modes, or maybe particles have to choose whether they want to be in one mode or in the other, right? So the state on the right is much more correlated, of course, and I think it's intuitive that it describes a pretty different physics. Okay. So in this slide, I'm presenting really the model we studied. You can see a Hamiltonian, which very much looks like the one before. So we have an pair interaction in the main field scaling, but we fix a very precise form of the external potential, namely a double well potential, as in the title. Which one? It is this curve in red. So we take two centers, XL and minus XL, which are distant L. And we take a homogeneous trap around those, okay? And these traps intersect at some point. So we take the minimum between the two traps. And we study the ground state problem of this system in the limit n to infinity, as before, so large bosonic system, and L to infinity, so a genuine double well potential, right? If we keep L fixed, we are in the same setting that we had before, like a external potential with some structure, but okay, fixed structure. If we send L to infinity, we have the two wells are infinitely far apart, and the height also tends to be infinite. Okay, so what will be the two modes that the system wants to occupy? Well, to the 0th order, we can say that one wants to be localized in one well and another in the other well, right? Okay, one should be more precise about that. And, I will try to do that. So it's still very relevant is the Hartree functional, which is defined as before, although with the double well potentials here. And we define EMF as its minimum with minimizer, which we call U plus. Okay, so U plus is unique up to a phase. And it turns out that if with U plus you define this linear operator in brackets, so minus Laplace plus B double well plus convolution. Okay, so it's called the infinite Hamiltonian or effective Hamiltonian. Then U plus, it is also the ground state of this Hamiltonian. This is not that difficult to see. It is an eigenvector, but it is in particular the ground state. Okay. And since H main field has compact resolvent, right? Because this external potential still grows double well, but in particular for any fixed L, it grows at infinity. We can write a spectral composition of the main field Hamiltonian in terms of eigenvalues only, eigenvalues and eigenvectors. So as I said, already by definition, we call mu plus the ground state, the lowest eigenvalue with eigenvector u plus. Then the next one we call u minus with eigenvalue mu minus. And then we have all the excited modes. So the picture you should keep in mind is that now this is the part of the spectrum of the mean field problem. These are the modes that matter to the leading order. Okay, particles want to occupy U plus and U minus much more than the excited modes. Well, why? How can one say that? Yeah. So this, let's say, turns out from the results I will show. But to get the idea, one should know information about the gaps of this Hamiltonian. So what is the energy cost in passing from here to here and in passing from here to here, right? So this should give an idea on how these modes are divided in energy scales. And this is what we did in a actually separate paper in which we really focused on the one-body problem. So we literally studied the quantities that you see in this slide. The crucial parameter that captures a lot of the properties of this effective model is this tunneling parameter T. So we call T by definition the e to the minus this fraction, which so S is the power of the trap, okay, and e to the minus 2 divided by this number L. So this power of L divided by 2. And for those who know this, this is equal to e to the minus 2 argmon distance within the landscape x to the s at the point L divided by 2. Okay. So since L goes to infinity, you should keep in mind that T is small, right? As soon as L grows, T will be small. And the key point is that T not only controls, but captures the first gap. Okay, the first gap is of order T. This is, if one knows a bit of semi-classical analysis, maybe this is not that surprising. And okay, it captures it for us up to corrections, which can probably be improved, although I have no idea how. All right, so, and yeah, this was the first gap of the midfield Hamiltonian. While the second gap, so if you want to go from here to here, you pay constant of order 1, at least. Okay. So this is the structure of the energy scales. And we also proved that the first two modes, when you take the absolute value, they are closed in many reasonable norms. And even more, we proved that they look like this curve in red. So this should be U plus in red. It continues below the blue. And U minus looks like the curve in blue. Of course, they don't stop here. They decay, but okay, my picture is bad. Okay. And so it is maybe not super surprising for you that if I take linear combination with the plus and the minus, one will be in the right well and one will be in the left well. Okay. Because of this, right? The profiles are basically the same, and only the sign changes in one of the two wells. So these results are actually very much inspired by results that were already present in semi-classical analysis, maybe from the 80s, or, yeah, 80s, 90s, especially by the school of Barry Simon and Bernard Alfer. Although they were definitely not present in our, let's say, the setting we needed. And in particular, we had to work a lot to get this lower bound in the gap. This is maybe the less trivial part. And also an observation by Mathieu Levine and one of his students helped us correct a mistake in an early version of the paper. All right. Okay, so this is the effective problem. And I'm now ready to state our first main result. I will use the usual CCR algebra of A and A dagger, which was already used a lot this week. And in particular, we call n left and n right the number operator for the mode left and the mode right. So let's see the result. We assume that the tunneling goes to 0 as some power of n, no matter what the power. And we assume that the coupling constant is small enough, of order 1, but small enough. And then, first of all, we prove condensation, basically. So the particles really occupy and the left mode and the right mode. Basically, asymptotically, they only occupy these modes, right? These expectations are n to the leading order. So this is what we wanted, right? We proved that two modes matter to the leading order. And then we prove this bound. Okay, we show that these two quantities, which are positive, are much smaller than n. So let's try to understand that. We are taking the number operator for particles in the left mode. We are subtracting its expectation value. It's not easy to see from here that the expectation value of n left can only be approximately n divided by 2 by symmetry. So this is the variance of n left, right? In expectation of the ground state. Now we know that from in the single well business, in single well setting, if L is fixed, expectations of this type should be of order n. This is the moral of the story of I mean, this is somehow implied by this result. What the expectation I'm looking at is somehow a square of an expectation of this type. So since I should compute the square of square root of n, I should have that the expectation is n. And what we prove is that this is not the case. As soon as L goes to infinity, like as some power, as soon as L goes to infinity fast enough so that the tunneling goes to 0 as some power of n, no matter how small. Okay, so this signals a breakdown of the means the independent and identically distributed picture. So signaling that the ground state is more correlated than for a fixed single well. Okay, and so our result has a twin companion, which is the energy expansion. So the energy expansion is in terms of quantities that I really have to discuss yet. So to the leading order, what has to matter is the restriction of the embodied Hamiltonian to the two modes that we want to matter into the leading order, right? So we project Hn onto U left and U right. This we call two-mode Hamiltonian. Okay, it does not have a particularly nice expression because it's a ugly combination of terms with creation and annihilation operators. But after some cleaning of constant and subleading terms, it looks like the Bose-Hubbard Hamiltonian, which you can read in either line. Yeah. So this is a very well-known model in which you have a hopping term, right? Particle gets destroyed on one mode and hop onto the other with a coupling constant, which is T, right? Roughly. So the coupling constant here is small, which means we are considering a regime of small hopping between the two wells. And then we have a on-site or on-mode quartic interaction with a coupling constant 1 divided by n, and okay, times a number, which can also be written as the variance that we want to be much smaller than n. And this will contribute to the leading order. And then we have all the rest of the modes, right? And we have to consider the appropriate Bogoliubov Hamiltonian for that. Now, if you have a bosonic system, there is a sort of well-known prescription to write down the Bogoliubov Hamiltonian, which probably dates back to Bogoliubov. So you subtract the condensate, the leading order part, and then you replace all creation and annihilation operators for the leading order part by their expectation, let's say, so square root of n divided by 2 in our case. And then you throw away a lot of junk. And what the quadratic operator that you have is the Bogoliubov Hamiltonian. And for us, okay, we can do it, no problem. It's a formal prescription after all. And then this operator splits into a left part and a right part, in the sense that the left part only sees modes which are localized in the left well, and the right part only sees modes which are localized in the right well. And how do they look like? And for H left, we have this expression. Maybe I don't have time to explain it that much, but it looks like a usual Bogoliubov Hamiltonian for particles in which can only occupy left well modes. And okay, one can consider the, let's say, lowest eigenvalue of H2 mode and the lowest eigenvalue of the Bogoliubov Hamiltonian. And let's call them E2 mode, E-Bog. And we prove that the ground state energy has this decomposition, okay? 2 mode part plus the Bogoliubov part plus constant remainder.
Can I ask you, the 2 mode part is of which order? Is it n to the 1 minus delta, or what is it? Because the T occurs in front of
the 2 mode energy, you mean E2 mode. So there is definitely a n order n, like a usual condensate energy, and then there is a Tn.
Yes.
Yes. And then, however, there are, so, and these come, so the order n part is somehow in these constants. So it does not come from a minimization of A and A target. What comes from the minimization is Tn. So this T times n from here. And all the rest is either a constant, which can also actually maybe be of this order, or subleading.
So when you say that T, I mean, you choose L to make sure that T is of n to the minus delta, you really want delta to be small, otherwise.
Yes, the smaller delta
is too large, then the true mode just disappears.
If delta is larger than 1, then that term is in the remainder. Yes. So I think that regime was already studied by Nicolas and Dominique, and indeed, they back in 2016, I think they could study it because they could throw away everything that happens between the two if the tunneling is much smaller than 1 divided by n.
But this corresponds to having weights extremely far apart. I'm confused.
Yes. So in the end, L has always to grow logarithmically, and it's some powers of log, something like that.
So if L grows too slowly, then you're in the usual limit. If L grows like a log, then you get this, and if L is really too, then become independent.
But so I would say that if L doesn't grow, I'm in the mean field limit. If as soon as L, so if
it grows very slowly, it's the same.
Maybe yes. It's when T is some log, But as soon as the power, then this result goes.
So if
okay. So I will try to give some ideas about the proof. So keep in mind that one has this picture, right? We have the two-mode part, we have the Bogoliubov part, and then we have all the difference between Hn and these two Hamiltonians, which are terms with one, actually also 2, 3, and 4 operators for excitations. So this is the usual picture. To prove the energy upper bound, one has to write down a good trial state and then consider the expectation. So here there is a mistake. It's going to be C trial. Let's look at the trial state. We have two indexes, S and D, right? You have to think that S is the index for how many particles are excited in every element of the sum. So the excited particles are described by this phi trial, which I will discuss later. And the remaining n minus s are either in U left or in U right. How are they distributed though? They are distributed depending on the index D, which is the difference between how many are in and in U right. So this n minus s plus d divided by 2 here, same with the minus here, and s excited. And then we have a further coefficient that depends on d. Now, what is this coefficient? Okay, it is a Gaussian in d with variance, this sigma square of n, which is always much smaller than n. So we make this choice. Sigma square is n times the square root of the tunneling. Since the tunneling is small, this variance is much smaller than n. And I cannot show it, but this is very much related to the fact that our ground state turns out to have reduced variance. Okay, so it is a good trial state in particular because of this choice. And for phi trial, we make this choice. Okay, we take the vacuum of excitations and we apply two Bogoliubov transformations, which are the ones that diagonalize this Bogoliubov Hamiltonian and this one. Since the two Hamiltonian left and right had, they only saw modes either in the left or in the right, these two operators commute actually. So, right, the definition is, I mean, there is no problem like ordering or anything like that. And okay, this is the trial state. Then one, with some effort, one computes and gets the energy upper bound. Can I take 2 minutes? Okay. And so what is really, really difficult is the lower bound. The problem is that so within this frame, this picture of splitting, one would like again to throw away everything which is here, and then minimize the two Hamiltonians separately. And I showed you that from the two-mode Hamiltonian, one could actually get the variances that we want. And so if this thing in red was not here, then we could take this together with the upper bound and get everything. The energy expansion and the fact that the variance is much smaller than n. Or maybe if you want that this variance divided by n is much smaller than 1, because it would be controlled by only this remainder. But there are linear terms in our model that cannot be neglected. This is in contrast, I would say, usual one-well setting, which linear terms are used because of the choice of the minimizer on which you expand. And so the idea we have is to complete the square. Okay, we have instead of minimizing this with passing directly to its minimum, to the minimum energy, we keep it. It is a quadratic operator, and we take these unwanted linear terms, and we shift creation and annihilation operators by a constant term in order to get H tilde, a new H tilde, which is quadratic in new operators, shifted operators, minus the remainder of the completion of the square. And it turns out, because of the structure of the linear terms, that this is, again, the variance divided by n, but with a coupling constant, which is lambda squared. And here we have lambda, right? So if we plug this, let's say, as a lower bound here, we see that for lambda small enough, we can eat the lambda squared term inside the lambda term and still get that the constant in front of here is something strictly positive. And by what I said before, this is more or less like saying that you can neglect the red terms and prove the energy expansion and the fact that the variance is more. Okay, thank you very much.
Questions? Yes, Nils?
I was wondering, so you were comparing these two types of states, right? What you call correlated and uncorrelated state.
Yes.
Suppose you could imagine a third type of state, which is something like U1 tensor n plus U2 tensor n.
Yes.
Could you compare that to your states, and would you be able, by your results, to distinguish?
So this is one of the terms here, I think, right?
Yeah, for D large.
There are two different summands of our sum. I think when you put everything there and you put everything there. Yeah, but I think so. The fact that this is a good lower bound, the trial state, I think suggests that configuration in which you put everything there on the left and everything on the right and you sum, they are negligible because we put this Gaussian. This is a Gaussian in D, right? If the difference is very large, then that's very small. Yeah.
And could you say, when physicists say they do like a superposition of two condensates, what kind of state do they have in mind?
In this sense, or?
I think there are experiments where they prepare two condensates and they let them collide and things like that. You have an idea which kind of the three states that would be?
It's a bit difficult because you can also think of adding two density matrices that like a mixed state. That, I mean, I'm just saying that there are further possibilities, right? You can add two density matrices that are a condensate and a condensate. So I think, I always have difficulty in understanding if I read superposition of condensate, what can it be?
So if I understood well, you are very lucky that the variance appears in your energy.
Yes.
And that's how you got the result. But could you get a more precise result about the density matrices? And I think it's related to Nick's question. So what is expected on the one particle density matrix, and maybe even the two particle density matrix? and I suppose I have to look at these objects to detect really which quantum state they are.
Yeah. So I don't know if for us getting information on the state, okay, let's say so getting information on the state is complicated for a number of reasons. Then getting information on the density matrices maybe is easier than on the state, but so we have a number of problems with respect to the usual business, and one is that the Bogoliubov Hamiltonian probably does not have a ground state, because it is somehow translational invariant in the d direction. So yeah, it's difficult to say that for in the infinite system in Fock space, that what is the thing that goes here, that's difficult. And also the fact that we cannot really diagonalize exactly. We can only have the ground state energy, so we really don't have for the moment the control of the precise diagonalization of the excitation part, because of this technical, at least because of this technical problem with the linear terms. So yeah, I don't know if that answers the question, but these are things that prevented us from getting a lot of more things. And for example, it prevents us to get an estimate for the error. So the error is just some sequence that goes to 0.
Okay, if we have no more questions, so online there is no question, we can thank Alessandro again.